Hello, student. Welcome back to this topic of digital electronics. And in this session, I am going to explain uh, the design and the circuit diagram and the working of this dual slope analog to digital converter. So this dual slope analog to digital converter is a very important converter because this has many more practical applications. If a very short conversion time is not a requirement, then the dual scope ADC is the best choice. As we have seen in our earlier sessions, we know that this conversion time is a very important factor because some circuits have the a shorter conversion time, but some of them have the longer conversion time. Always, the shorter conversion time is more preferred, but sometimes even a circuit with longer conversion time is also preferred for some other reasons. This dual scope EDC is having a very short conversion time. No, it is having a long conversion time, but it is having some other good properties like it offers good accuracy. It offers the good accuracy and good linearity. So accuracy wise, this is very good. Means your analog input will be accurately converted into digital one, and good linearity means the input and output are having a good linear relationship, and it has a good noise rejection characteristics. There is no problem with the noise in the circuit, and it has a very high resolution. So this is a very important factor. Because of this parameter, the conversion time of this circuit is little bit longer, because these two parameters have the inverse relation. If you are increasing the if you are decreasing the conversion time, then the resolution will be high, and if you are trying to decrease the resolution, you can have the very low conversion time. So in this way, the conversion time and this resolution are have a universal type of relation. So it has a very high resolution, and it is economically very viable. So it is very cheap. You can construct this circuit very cheaply. No more expenditure for this. And its only disadvantage is that its conversion time is very high. As I told, this high resolution is the very important factor, because this ADC is constructed to have a very high resolution, and because of that reason, the conversion time becomes longer. So this is the main disadvantage. So the only disadvantage is that its conversion time is very high, and because of this reason, it's not used in data acquisition system or in signal processing systems, and it is used in a digital voltmeter, ammeters, panel boards, etc. So wherever because of the more accuracy of this circuit, this kind of applications come out from this circuit, and mostly it is used in digital voltmeters, digital ammeters, or panel boards, etc. And this dual slope ADCE uses an op-amp based integrator as a dual ramp generator, and its construction is as given below. So this is the circuit diagram of an op-amp based, operation amplifier based integrator. So here input is given to the inverting terminal of this op-amp, and here we have an input resistor, and this is important to see here. So here in the place of feedback resistor, a capacitor is connected. So because of this reason, it gives this integrating action. So the output of this integrator is given by 1 by C times the integral of IDT. So that means actually this circuit counts the number of charges which are varying with respect to time. So, and hence that means it measures the current, or this can be written as VI divided by RC into T, where VI is a constant. So this is the output of this integrator circuit. So this integrator circuit is used as a ramp generator in this dual slope ADC. So this is the construction of dual slope ADC. So it consists of four important parts, and this is the integrator. This is the integrator, and this is the comparator, and this is an AND gate. It is a binary counter, and here we have the output latch for the storage purpose, and here you are getting a digital output. And here, so the input is given here as an input to this integrator, and during the first half cycle of the analog input, the input signal is integrated, then the proportional output is given, and that output of this integrator is given to the comparator as the input. So when the output of this integrator is greater than this 0 volt, because it is connected to the ground, this comparator works, and it will be having some output. And whenever there is output at the output of this comparator, this clock connected to this AND gate is allowed to pass through this AND gate, because here one of the comparator input becomes 1, and when this clock is on, it also 1, and when both the inputs are on the on state for the AND gate, then only its output is on or 1. So because of this reason, so when the clock is on, the output of this integrator should be 1. So that 1 1 leads to the output 1, and this clock is allowed to reach this binary counter. And as soon as the this clock reaches this binary counter, the binary counter starts counting up to certain time, and then it get reset, and the output of this binary counter is connected to this output latch. So this output latch consists of RS flip-flops or that kind of things. and this latch is used to store the information, and the digital outputs are obtained here as the output of this latch circuit. So this is how the circuit works. And this input voltage, initially the input, when the input voltage is first connected to the integrator, the signal is integrated to certain time. Then there will be output across this integrator, and the comparator becomes on. Or the comparator will also have the output. But what happens at the end of integration? Once integration is over, this variable terminal is switching over to this minus VRF. So here minus VRF is the reference voltage, and it is connected to the reference voltage. And now the reference voltage is going through this integrator. And since it is a negative reference voltage, the output of this integrator is integrated in the positive direction. But when this input analog voltage is connected to the integrator, since it is a positive voltage, but here it is a negative terminal, inverting terminal is there. So the output of the integrator will increase in the negative direction. But when the negative reference voltage is connected, then the output of this integrator will be in positive direction. So in this way, two cycles are there, one during the negative half cycle and next during the positive half cycle, and one complete cycle is used for the conversion process. So the circuit diagram for dual slope ADC is as shown above, as I explained now. And in dual slope ADC, the integrator generates two types of ramps, one with known analog input voltage VA, and the other with known reference voltage minus VRF. As I told, two ramps are generated, and these two ramps are having the ramps are nothing but two slanted lines, straight lines with opposite slope. One ramp is having the positive slope, whereas the other is having the negative slope, but the slope will be constant throughout the line. So that is the very, very important thing. So two ramps are generated for every cycle in this ADC as output of the integrator, and one ramp will be increasing in the negative direction, the other ramp will be increasing in the positive direction. So the working of this this ADC is like this. So the binary counter is initially reset to 0, 0, 0, 0 if it is a 4-bit circuit. If you are designed the circuit for a 4-bit, it is reset to 4 zeros. That means all inputs are at 0 level, and the output of the integrator reset to 0 volt. At the ramp generator or integrator, the input voltage VA is set to some unknown value, and the analog input voltage is integrated by the inverting integrator and generates a negative ramp output. So what happens? The input voltage, when the input voltage is given to the inverting terminal of the integrator, and during the first half cycle, it is a negative cycle. The analog input is integrated by the inverting integrator and generates a negative ramp. So negative ramp is generated because of the first half cycle. Next, the output of the comparator is positive at the end of first half cycle, and the clock is passed through. The clock is passed through the AND gate, and this results in counting up of the binary counter. So when the this output diagram is shown here, the output diagram of the integrator is as shown here. So when you are here, the integrator is reset to the input voltage VA, and the input voltage is positive here, but you have given that to the inverting terminal, so the output is negative, and the output increases in this way with the constant slope, and the slope is given by minus VA upon RC. And this ramp increases up to the reference voltage Vs. So that this increases up to a certain fixed reference voltage Vs. The negative ramp continues for a fixed time period T1, which is determined by a count detector for the period T1. So you can see here, this is the negative ramp. And this negative ramp continues for a fixed time period T1. Here this time period, this T1 is fixed, and up to end of this time T1, the ramp will be increasing. And this ramp will be increasing in the negative direction, because even though your input voltage is a positive voltage that is given to the negative terminal or the inverting terminal of the op amp, and hence the output increases in the negative direction. So the negative ramp continues for a fixed time period T1, which is determined by the count detector for the time period T1. At the end of the fixed time period T1, the ramp output of the integrator is given by. So at the end of this negative ramp, so this is the negative ramp, it starts here and it ends here. At this point, what happens? So when just a minute. So the negative ramp continues for a fixed time period T1, which is determined by the count detector for the time period T1. At the end of the fixed time T1, the ramp output of the integrator is given by this equation, Vs is equal to minus Va upon Rc into T1. Next, when the counter reaches the fixed count at a time period T1, the binary counter resets to 00 and switches the integrator input to a negative reference voltage or V reference voltage. So this you can see very easily here, or we can see, we can go to the output of this this ramp generator. It is like this. So here the ramp increases in this direction up to Vs. And once this point is reached, the counter resets. The binary counter counts up to this point, and here it resets, and it starts increasing in the positive direction in this way. So the negative ramp continues for a fixed time period T1, which is determined by the count detector for the time period T1. So this is the negative ramp up to time period T1, it increases. And so at the end of the fixed time T1, the ramp output of the integrator is given by this equation, Vs is equal to minus V upon Rc into T1. When the counter reaches the fixed count at a time period T1, the binary counter resets to double zero zero zeros and switches the integrator input to a negative reference voltage. And this happens like this. So here, this is the point. And once the ramp increases for a fixed time period T1, at the end of T1, the integrator switches, and it switches to this negative reference voltage. So that negative reference voltage is given by minus V upon Rc into T1. And next, when the counter reaches the fixed count at a time period T1, the binary counter resets to 000 and switches the integrator input to a negative reference voltage. And now the output of the ramp generator starts with initial value minus Vs and increases in positive direction until it reaches 0 volt, and the counter gets sorry, just a minute. So after the end of the what is that? Negative input voltage, positive input voltage, the integrator switches to a negative reference voltage. Now the output of the ramp generator starts with initial value minus Vs and increases in positive direction until it reaches the 0 volt, and the counter gets advanced. So that we can see here. So this ramp increases until this point is reached. So it is minus Vs point. And from this onwards, it resets and it starts increasing until it becomes a 0 volt. That is the time period T2. So actually this is the time period T1 and this is the time period T2. Missing is there. And so the binary counter resets to 000 and switches the integrator input to a negative reference voltage. Now the output of the ramp generator starts with initial negative source voltage and increases in positive direction until it reaches 0, and the counter gets advanced. So here it is minus Vs at this point, and next for next cycle, the counter increases in the positive direction until it reaches the 0 volt. 0 volt is here. So this is given by and at this point comparator output becomes negative and the gate is deactivated, and hence no further clock is applied through the AND gate. And what happens here? Here the comparator gets resets, and when it reaches 0 volt at this point, and one cycle completes, actually the actual conversion of the analog signal into digital signal starts from this point and it goes up to this point. And because of this reason, this time period T2 is not a fixed one, but whereas the time period T1 is a fixed one. And this so next, when Vs reaches 0 volt, the comparator output becomes negative and the gate is deactivated. And now and hence no further work is applied. No further clock is applied through AND gate. And now the conversion cycle is said to be completed. And the positive ramp voltage is given by Vs is equal to V reference node RC into T2. Where this V reference and RC are constant and time period T2 is variable. And the amplitude of positive and negative ramp voltages are equated as they are given by as their LHS is same. As its LHS is same, we can equate its RHS. So this is for time period T2 and this is the time period T1. Equate and you can cancel this RC. You will get T2 is equal to minus VA upon VRF into T1. Or you can write this as a VA is equal to minus VRF into divided by T1. So what happens? The actual conversion of the analog voltage VA into a digital circuit occurs during the time period T2. The binary counter gives corresponding digital value for time period T2. The clock is connected to the counter at the beginning of T2 and is disconnected at the end of the T2. Thus, the counter counts digital output voltages as given by the digital output is equal to counts per second into T2, or you can write this as digital output is equal to counts per second into this time period T1 or T2. This time period T2 is written as T1 into VA upon V reference. So this is the output of what is that? This kind of a dual slope ADC. So this dual slope ADC works nicely when you have some reference voltage and variable or the input voltage, and accurately this ADC converts the input signal, analog input signal into a digital one. And digital output is taken from here. As I told, the circuit is very, very important because it does the many important works, and hence it is used for a large number of practical applications. So this is about dual slope ADC. Thanks for watching.